Hi class, so we continue our previous lecture, okay, about the stages in the formation of the stars. Okay, now we continue with the stars of the other masses. So the numerical values and the evolutionary track just described are valid only for the case of 1M star. So the temperature, density, the radii of the pre-stellar objects of other masses exhibit a similar trend. Okay, but the more massive the fragments produced, the more massive the protostars. So also the main sequence. Okay, so whatever the mass, the end of point of the pre-stellar evolutionary track is the main sequence in the middle. Yeah. Okay, so the zero age main sequence, we have the evolutionary track of 0.3 m star and 3 m star are quite similar to the track of 1 m star. But the lower the masses, the more time is required for it to be formed. For O-type stars are formed in a very million years, while M-type will require billion years to form. So a star is considered to have reached the main sequence when hydrogen burning begins in its core and the star's properties settle down to stable values. Therefore, using the mass and the initial condition, the theory predicts a zero-age main sequence, ZAMS, and it agrees very well with the actual main sequence line observed for stars in the vicinity of the Sun. If all gas clouds contain precisely the same element, okay, in the same proportions, so mass would be the sole determinant of a newborn star's location on the HR diagram. However, stars with more heavy elements tend to be cooler and slightly less luminous than stars that have the same mass but contain fewer heavy elements. The important notes here, the main sequence is itself not the evolutionary track, but just a point where stars stop and spend most of their life keeping pretty much the same surface temperature and luminosity throughout the time. The star will only move away from the main sequence at the next stage of the stellar evolution. Okay, so the stellar evolution will be discussed in the next chapter. Okay, so we have also the failed star. What happened? Because of the nuclear ignition, okay, rest of the gravity to crush its matter to the point of this nuclear ignition. And the low mass gas fragments like this continue to cool, eventually becoming compact fragments, okay, so unburned matter. So that is all the condition for the failed star. And we have the minimum mass of gas needed to generate core temperature high enough to begin nuclear fusion. Okay, so about the nuclear fusion reacts in its core. Okay, the vast number of substellar objects are frozen in time somewhere along this contraction phase. Okay, and the such object with mass more than 12 m are known a brown dwarf, while anything smaller is simply called a planet. And this faint and low mass brown dwarf are difficult to study. There may be up to 100 million. Okay, next. About the cloud fragments and the protostars, we have never seen any individual object going through the starbird since the age of our entire civilization is much shorter than the time needed for a single interstellar cloud to contract and form a star. However, we can observe the interstellar clouds, the protostars, and the young stars as they appear today at different stages of their evolutionary path. So the evidence of this cloud contraction, we have the pre-stellar object at stage 1, 2, can be observed via radio emission, okay? And the emission nebula are indicators of starbirds, the youthful orbit stars that energize the nebula, and also the Trifid Nebula M20 is the analysis suggests that this region of the greatest molecular abundance is also contracting and fragmenting. And also the huge dark molecular cloud surrounding the visible nebula equals to the stage 1 cloud, the low density and the temperature, okay, obscured the regions A and B here. Okay, these regions A and B is a denser and warmer fragment, okay, in the stage 1, 2. The Doppler shift of the radio lines observe the vicinity of region B equals to the fragment contraction, and the anti-nebula refer to the stage 3. The central star is in a stage of 6 to 7 for the full star. Okay, so the evidence of cloud fragment. Okay, the Orion complex is lit from within by several all-type stars. The bright Orion Nebula is partly surrounded by a vast molecular cloud. Okay, we have DNE is a protostar here. DNE is the protostar. Okay, on their way to the stage 3. And for stage 4 to 6, objects shine more strongly. Okay, continue. For the stage 4 to 6 is an object shine more strongly in the infrared. Okay. Okay, now we have this Becklin New Gibbor object, okay, BNO, a bright infrared emitters in the core of the Orion molecular cloud, and is covered by these American guys here. And it has the high mass protostar around the stage 4 with luminosity here. Okay, for the low mass protostar with infrared heat signatures of an object of Hayashi tribe in stage 5 was spotted by the Hubble Space Telescope in a rich star-forming region in the Orion. So the evidence of protostar is the energy sources for some infrared objects seem to be luminous in stage 6 hot stars, okay, meaning the large amount of UV radiation they emitted are mostly absorbed by the cocoons of dust surrounding them, and absorb more energy is then re-emitted by the dust as infrared radiation. Okay, so these bright infrared sources are known as the cocoon nebula. Okay, we predicted to disperse quite rapidly once their central are formed. Okay, now is the protostellar winds. Okay, the radio and infrared observation of H2 and CO molecules in the Orion Molecular Cloud reveal a strong winds, okay, and expanding outward at the this velocity. Okay, here you can see the strong wind, and these protostellar winds are related to the violent surface activities associated with many protostars. The strong heating within the turbulence disk, okay, this is the turbulence disk, okay, and a powerful protostellar wind combine to produce a bipolar flow, means in two direction here in this figure, expelling two jets of matter in the direction perpendicular to the disk. So as the protostellar wind gradually destroys and blows the disk away, the outflow widens until the wind flows away from the star equally in all directions, like here. So this Herbig Haro or HH object, okay, here are turbulent looking patches of associated with the newborn stars named after the investigators who first cataloged such object. Okay, who the one who found this feature, okay, this HH object. So in the Orion Molecular Cloud, a newborn star is surrounded by a bright nebula, its turbulent wind spreading into the interstellar medium. So the twin jets HH1 and HH2 travel outward from the unseen protostellar disk and collided with the surrounding interstellar matter. So about the shock wave and star formation, many kind of the cloud, fragment, protostars, stars, and nebula in the interstellar medium interact in a complex fashion, okay, which affecting all the behavior of all others. So the outward expanding matter wave driven by the high temperature and pressure in the nebula is known as the shock wave. Okay, it may crash into the surrounding. Okay, so the shock wave are thought to be the triggering mechanism needed to initiate the star formation. So when a shock wave hit the interstellar cloud, it races around the thinner exterior more rapidly than it penetrates its thicker interior. So this squeezes a cloud from all directions and causing the implosion. Okay, so the generators of the shock wave include the emission nebula, the planetary supernova explosion, spiral arm wave, and the interaction between galaxies. Okay, what is the supernovae? Okay, supernovae are the most energetic and efficient generators of shock wave. However, they are relatively few and far between. In other words, the birth of stars is often initiated by the violent and explosive death of other stars. And generally, the orbit stars are the main drivers of star formation. Okay, which means they form quickly, live briefly, and die explosively. So this new shockwave can produce second generation stars, and the process continues like a chain reaction. Okay, as can be seen here, the newborn stars and happen the expanding shockwave between this area in all direction, and got the first generation of the stars and also the new generation and the next generation of the star. Okay, so this group of stars nearest to the molecular clouds appear to be the youngest, whereas those further away seems to be the older one. In a star-forming region in the galaxy, okay, this name of the galaxy, a series of bright emission nebula powered by hot young stars can be seen. Okay, the end of the result collapsed cloud is a star cluster. Okay, star cluster is a group of stars all formed from the same parent cloud and lying in the same region of space. That is the star cluster. So this star cluster form at the same time out of the same cloud, okay, and the same environment condition. The only factor distinguishing them is mass. Okay. And we have also this Pleiades or the Seven Sisters is a well non-naked eye object in the constellation Taurus. It is an open cluster, a loose and irregular cluster shape. If you can see this figure, it's a loose and irregular in shape. Yeah? That is the example for this open cluster. Still in a group of star. Okay, so these open clusters are found mainly in the plane of the Milky Way. Typically contains 100 to 1,000 stars, yeah, and a few parsec across. So the cluster and association, the HR diagram shows that the Pleiades cluster contains stars from all parts of the main sequence. Thus, we can estimate the cluster age, and the leftover gas is further evident to be the cluster relatively young, and the system is abundant in heavy elements that could have been created only within the course of many generations of the ancient stars. The less massive but more extended cluster are known as the association, which means having no more than 100 bright stars but spanning tens of the parsec. So the association are rich in very young stars, for example, the T association or the OB association. So the main difference between the association and the open clusters is the efficiency. So efficiency of the star are formed from the parent cloud. Okay, the globular cluster is roughly spherical, generally found away from the Milky Way plane and contains millions of stars. Okay, like this figure is the Omega Centauri, and is lying about 5,000 parsec from Earth, okay, via the spectroscopy parallax method. And the globular cluster are known to have a lack of upper main sequence stars. Okay, the more massive the OBAF stars have long since exhausted their nuclear fuel and moved from the main sequence to become the red giant. How about the A-type star? Is shown are known to be a stars at much later stages in their evolution that just happen to be passing through the location of the upper main sequence. So most globular cluster contain really the old stars, okay, and can estimate at least 10 billion years old. So only a few heavy elements in that cluster, and 150 globular cluster observed today are just the survivors of a much larger population of the cluster that formed long ago. Although the main stages in the formation of the individual stars are becoming clear, the earlier stages one to are still sketchy. So in general, the more massive the collapsing region, the more stars will be formed. And low mass stars are much more common than the high mass one. For every OB type giant, 1,000 of GKM type dwarf may form, and about the efficiency determine the amount of leftover material, and the formation of the OB stars is speed up the dispersion process. Okay, now we have these close encounters And the collisions between the protostar within a star cluster may be very important in determining the properties of the stars. So the stars tend to be formed as small groups in dense pocket of gas, and it can disrupt the smaller protostellar disk, determining the growth of the central protostars, ejecting the planets and low mass brown dwarf from the disk into the intra-cluster space. This is the cluster environment. Okay, so the first few massive bodies to form tend to pretend the formation of the additional high mass by stealing their raw material and disrupting the environmental in which other stars are growing. So this explains the existence of the brown dwarf, that they either face this destruction or gas dispersion, before the nuclear fusion could begin. So here is the brown dwarf, and we can see the ejected stars. Okay. And also we have the trapezium. Trapezium is a group of 4 bright stars responsible for ionizing the Orion Nebula. The infrared image reveals an extensive cluster of stars that is showing many stages of the star formation. Okay, and the green fuzz here, you can see the jet of gas from the young stars that collide the surrounding cloud also here. Okay, so eventually the star cluster either dissolve into individual stars or loose gas become the gravitationally unbound and disperse. We have this tidal gravitational field of the Milky Way. Okay, and loosely bound association may survive for only 50 million years, whereas very massive open cluster can live up to 5 billion years. So that is the cluster lifetime. Okay, so this is the recap of this chapter. So we have learned about the sequence of the event, for the formation of star, how the formation of star depends on its mass. Some of the observational evidence support the modern theory and the nature of interstellar shockwave, and their possible role in the formation of star. And lastly, we have why star form in cluster and difference between open and globular star cluster. Okay, that's all for today. Thank you.